Hello, it's Keith here, and this is lesson 3 of my IBM370 assembly programming tutorials. Now, we've looked at some simple commands, we've looked at the addressing modes, and this time we're going to go into some more details of basically how to call subroutines, and this also brings in the concept of save areas, which is kind of a snazzy way of referring to the stack. It works a little bit differently to a regular stack, but that's basically what it is. So we're going to do that. We're also going to look at some compare commands. So let's go over to our code and let's fire up our server. So what I would recommend is before you get started is to use the hello example, because the more complex ones can overload the server as it's starting up basically. So we're using this hello JCL, and the command you want to use is the Hercules job, just the regular Hercules job without the header and footer. Now I've changed the message so that instead of IBM this time it says I like cheesy peas, and the reason it says that, it doesn't need to say cheesy peas, but I've changed the text so that we can tell if the server is showing new information or is still showing the information from a previous execution. The servers are starting up off screen. I just need to leave them alone because there's some send keys commands that's going on there. But in a moment they will be finished. I think they're about finished, and we should see the output at the far right of our screen. This is the simulated printer output. Here it is, and you can see our I like GTP's message. So we know that is new information and is not being created from a previous execution because we changed the text it was showing. Okay, so our server, there's our terminal window. We don't need to use that. And here is our server window. We don't need to use that. We'll leave them off screen there. But the important thing is our printout over here. Okay, so we're going to be running lesson 3, and there's some branches here at the start of our code. We need to remove the comment from one of them. The star at the start of the line is the comment. The semicolon, as I said before, is just there to make Notepad++ color this nicely. So that's that. And we're running this subtest. Okay, let's fire it up and let's see what happens. Okay, our execution is running. Oh, I made a mistake. I selected Hercules job. I should not have done that. I should have done basic header and footer, because this is not a complete job file. This is just an ASM file that needs a header with the job start and also a footer with some commands that I use, the monitor functions basically. So I did that wrong. So learn from my stupid mistake there. Hercules job basic head footer if you're using my scripts. And okay, we've now got some output that looks like something might have worked. Okay, so what we've done here is we've shown subcolon. That was done by this print char for routine here. Now, of course, these are all executions to subroutines as well, but we're going to be looking at these specific MySub1, MySub2, and then MySub3. So BAL is branch and link. Now, this is a sort of familiar concept if you've come across the RISC systems like the ARM and RISC-V, things like that. But this wasn't something that was really a thing on the Z80, so we'll explain it again. So basically, this executes the address specified, and it puts the return address in a different register, R14. So when we run MySub here, the return address will be in R14. And if we look at MySub here, the MySub basically is loading this sequence of characters here. And then what it's doing is it's storing those into the address in R11. Now, R11 is used by my tutorials as basically a pointer to the current line of text that's about to be dumped to the screen. And then what we're doing here is we're incrementing R11 by 4 bytes. And then the reason we're doing this rather than using a subroutine is because nesting of subroutines will cause us some problems. So we're not doing that in this case. So there's no nesting of subroutines here. Now, when we want to return from this subroutine, the return address is in R14. So we use the branch to register command to branch to the address in R14. And this is effectively the return command. So this will return from that and returns back up to here. So that will do the following command. Now, the problem would have occurred if we'd have used, for example, this print char for routine here within this subroutine. It wouldn't have worked right, because that would have also changed R14. So when we returned here, we would have probably ended up with an infinite loop, but we'd have certainly ended up with a bad program. Now, there's multiple ways we can get around this. One option is simply not to use R14 for the return address. Now, when we use branch and link with a subroutine address here like this, the assembler is actually converting this. This would have, in theory, be a 32-bit address, but we can never specify a 32-bit address. So it's always being calculated as an offset from the register that's being specified with using here. So this would actually be converted to something in this syntax here. Now R0 is a hardwired 0. There's an offset of 0 here, and there would be a base register. Now it would be calculating this offset of using R12 as the base, but in this case what we're doing is we are loading R15 with the address of my sub2 here. So that will be loaded in, and we're going to call my sub2, but in this time, instead of using R14 as the return address, we're going to use R9 as the return address. And this is one of the ways that we can get around the problem of nesting subroutines. So if we look at my sub2 does actually contain a subroutine call within it. It's using R14 as its return address here, and that's what print char4 expects. That's how it returns. But this subroutine here is actually returning using R9 as its return address, and I know R9 isn't being changed by the print char4 routine, and we've loaded R9 with the return address because of this branch and link here. So that is one option here. We can do this here as well. We could change this to R9 here, and we could then simply change the matching return address here, R9, and then we could actually just put this print char4 in here, and that would work just fine, because we now don't need to worry about changing R14. That will execute just fine. So you can see SB1, SB2, SB3, those have all worked fine. And so we can nest subroutines just fine. We just can't use the same register as the return address for the nested subroutines unless we do something to preserve the original value in that return address here. Now the third version here, we're doing the same again. We're loading the address that we want to call into a register, and we're using that with BALR. So branch and link register this time. So this time the address is in a register itself, so no longer specifying a base and an offset here. And the return address again in R14. Now this time we've done our call in a different way. This time we're using R14 again to branch and link to print char4, which will corrupt the return address in R14. But as long as we in some way preserve that return address, we can still function just fine. And so in this case we've preserved the return address in R14 by simply loading it into R9 here, and then returning by branching to the address in R9 here. So that's our return, even though we executed linking to R14. So that all works just fine. Now obviously, you know, this is a bit of a pain here, you know, having to remember all of these addresses and which address is our return address in, what's our subroutine expecting the return address in. That's all a bit of a pain. We really want a nice simple solution that we don't need to worry about that kind of nonsense for. So, well, what can we do? Well, the simple solution is we can use the save area, which is basically like the stack temporary store for our values. We use the command stm, which is store multiple. Now this takes a range of registers and it stores everything between those two registers. So when we use R14 here, that will basically do R14, R15, R0 and R1, and it stores those in the register in the address specified in a register R13. Now the problem is that basically we need to then allocate some free space in case we then call a subroutine that does the same thing. Now the way that this command is storing these very specific set of registers here, but depending on what command we execute, we might find things work a little bit oddly. So in general terms, I would recommend you always allocate 72 bytes. So we're effectively incrementing the address in R13 by 72 bytes here. And so that is allocating enough space for as many registers as could possibly have been stored here. I'll explain why that is the correct value in just a moment. Now what we're doing here then is, now that we've basically backed up R14 and R15 and a few others here, we can now do whatever we want with R14. So we're using branch and link here. We're running multiple commands here within my sub4. And then when it comes to return, all we need to do is we need to restore the value in R13, subtracting the 72 that we added up here, moving us back to the original position, and then we're loading the multiple with the same register specification from R13 here. So load multiple here is the companion to store multiple here, and because we've specified the same range, R14 has now got the same return value, and we can return from this subroutine just fine. And this subroutine 4 here, you can see, has shown the contents of these registers to the screen here. Now, well, what actually happened here? Well, during this subroutine, you see, we've loaded R0 with A0, 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 R1 with A1, 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 and R2 with A2, A2, A2. And then we've returned here, and basically we've shown the contents of the registers before and afterwards. Now, before, you can see F0, F1, F2, F3 here. These are the values loaded up here. And then in the next line, you can see A0, A1, A2, and F3. But then after the subroutine, you can see that register R0 and R1 have been restored, but R2 and R2 has not. Now, the reason R2 has not is we changed R2 here, but it wasn't specified in the range of registers that were stored and restored. Now, we could change this and we could preserve the value in R2 if that's what we want to do. Depends what our subroutine is doing. Maybe that's the return value of the result of the functioning of the subroutine. Maybe we simply don't care what value's in there. But here we can now preserve that. And you can see that A2 now has been reset as well. So really just depends on the range of registers we specify here. Now, why are we specifying 72? Well, part of the reason for that is in most cases, rather than using STM and LM, we might want to use the save command and specify a range of registers here, and the return command and specify a range of registers. Now, the return command here is also doing the branch return here as well. So this is effectively a load multiple and a branch return to R14. This is assuming the use of R14. Now, this actually uses an offset when it stores the registers, and what that offset is actually depends on the range of registers we're specifying. At least to my understanding, I did some testing on this, and my understanding of it, I believe, is correct, but I am no expert on this system. But basically, this is making some quite curious assumptions about that save area. So the fourth 32-bit value will be register 14, the fifth will be register 15, the sixth will be register 0, and so on. But the first two will actually be reserved for other purposes, basically by the operating system. So these are used by debugging tools, and so whatever we store, we might find it's not stored in the position that we expected, and we might find that it doesn't use the number of bytes we expect. So I would, as I say, unless you are finding memory a problem, I would strongly suggest you always add and subtract 72, no matter what you're actually saving and restoring here. That would be my recommendation, as I say, just for simplicity. Now, as I say, before with my sub 4, we were using store multiple and load multiple. My sub 5, we've done a very similar thing here, but we've used the save commands here and the return command. These are macros that convert into various commands. And so you can see here we've run my sub 5 and we've monitored again. Now my sub 5 has loaded these B values into the registers here, and you can see them here. But you can see they've actually all been reset here because when we've saved and returned, we've specified basically a full range of registers here, and from 0 to 15. Now, if we'd specified a range where the bottom register was something like 14 and to maybe 2 or something, let's just use 1, so 14 and 1, which will roughly mimic what we did before. So this would back up registers 14, 15, 0 and 1, and if we run this again, and then we'll find that registers 2 and 3 here will not have been reset here. So R0 and R1 now contain the F values again because they've been reset, but 2 and 3 now have been left unchanged. And so, as I say, it's a consecutive range. So if the first value in the return command or the load multiple command is higher than the second one, it doesn't go in descending order. It goes 14, 15, 0, 1, and so on until it gets to the second register value, which we can exploit to back up register 14, which is our return address, and 15, which is our using address, and then there's low registers. So that's how we can use that. So very handy there. Now, as I say, in most cases, I would strongly suggest you sort of play around with these yourself. But with the last example, especially, I think that's essential. We're going to be looking at some conditions, but I only do a very small number. I strongly urge you to try them out yourself if you're interested, because I couldn't understand these from just reading bits of text online or books and things, so I think you do need to try them out yourself. Anyway, we looked at some branches and links there, so effective calls to subroutines, but there's a very special macro and a special call type, which is the service calls. Now, we're going to use here the write to operator. Now, this is what I actually use to get all of my text to the screen anyway. The write to operator macro actually converts to a service call, and I use that service call in my tutorials to get text to the printer. This is actually the printer output here. I keep calling it the screen, but it's actually the printer output. So what we're going to do here is we're going to use the write to operator macro to print hello mum to the screen, and you can see that just there. But then what we're going to do is we're going to basically expand that. I've looked at the listing file that this assembly creates, and what it basically does is it creates a block of a code, of byte code, with a sequence of commands that print the message to the screen. So this is effectively the sequence of commands that are created when we use that write to operator macro, and it is actually a function call to service call 035, which is an octal here. So if you want to know about these service calls, you have to go and read all of the IBM documentation. I haven't really done it. I only know the ones I've needed, which is really just this one. So what's all of this do? Well, this first command here is ensuring we're aligned to a 16-bit boundary. This is then specifying the length in bytes here, so 14 bytes. This is a set of flags here, so that's just a 0. Then we've got the text we want to show. The C here specifies a character. And then finally, we're ensuring we're 16-bit aligned again so that the following code runs correctly. And so this service call here is showing the string at the address pointed to in R1. And if you want to know what these service calls do, as I say, you have to read the documentation to understand them. But in our case, we've shown hello mum and hello dad. Now, when we're using all of my monitor functions and these print lines and things, what we're actually doing is we're sort of poking characters into a long empty string within my code, and then when we do the print line routine, that is calling a write to operator command macro here using that service call. So that's what's going on behind the curtain, so to speak. So there we go. So that's a special kind of call. Depending on what you need doing, you'll probably need that. But as I say, you will need to read the technical documentation on the operating system to know what it does, because it's all platform specific. Now, we've looked at how to do addition and subtraction before, and we're going to look at how to do branches based on conditions in just a moment. But before we do that, I think it's worth discussing the simplest and arguably most convenient function for conditional stuff, which is the count functionality. So what we can do is we can actually use a register, in this case R1, and we can use a special branch and count. So this is like your decrement and branch kind of commands on other processors. But what this is basically going to do is it's going to effectively in one go decrement the register specified R1, and it's going to branch back to the address specified, loop in this case, if that is non-zero. So what we're going to do here is we're going to show the contents of R1 and a few of the registers to the screen here, and so we can see what actually happens here. So basically what we're doing here is we're loading the count register with R5, and we're showing this to the screen throughout the loop. So here you can see R1 contains 5, 4, 3, 2, and 1. Now, when it reaches 0, there's no branch back, and so we don't show that one. So this has continued until we got to 0 here. That loop has continued until 0. Now, that's a very simple count, but the IBM370, it has some really quite incredibly complicated commands in some cases. Now, this command is branch on index less than or equal, and you might think this is just doing some simple comparison and repeating, but you would be wrong. Now, we're specifying a total of 2 registers here, but the second register specification actually implies a third. Now, what this is basically going to do is R1 is our counter register, the register that is changed, but then register 2 specifies the amount that is going to be added to register 1, but then register 3, the register immediately following the second one. So by specifying R2 here, we're implying R3, and that is the end condition. So what we're basically saying here is R1 is going to start at 10 in hexadecimal. We're going to add 3 each increment specified by R2, and we're going to continue as long as R1 is less than R3, and so we're going to continue up to 20 in hexadecimal. So you can see here R1 contained 10 at the start. We were adding 3 each time, and our end condition is 20. And you can see here R1 went all the way up until it went over 20, at which point we ended. Now in this case, what we've done here is we've got our loop here, so we were showing the monitor each time, and then once we got to the end we put a blank line in and showed the final position of the registers here. So you can see the final position after the loop had ended was R1 contained 2, and so that was the end condition on branch on index less than or equal. We can also do branch on index higher, which kind of does things the opposite way. Now in this case we're going to use R2. Again, we specify just one register, R3 is implied. R2 this time is going to subtract 3, and our end condition is the original 1, 0 again. And so BXH, so this will repeat so long as R1 is higher than R3, subtracting R2 each time. And you can see here that R1 is going down, 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 and then when it gets to 1, 0, our condition has ended, and so again we've shown a blank line and shown the final condition position here, and so that's why that final value is shown there. So those are some convenient and in some cases extremely powerful condition options for using loops. Now what we're going to look at this time is various condition and commands. Now this is really where I'd strongly suggest you download the examples and try them out yourself. Now, I'd honestly suggest that every time, but in this case, I think you really need to. Now, there's basically an infinite number of permutations and combinations of the commands I could use here, and so we're just going to look at a few of them. Now, the first question is, we're going to have two values that we're comparing, but the question is basically, what are our values actually supposed to be? So here we're loading two 32-bit values, but the first question is, are these signed values, are they positive and negative, or are they unsigned values, logical values? Because if they're signed values, then this is a negative number, a very small negative number, but if they're unsigned, this is a higher positive number. And so that is the first important question we have to ask. Now we're using compare logical register here to compare these two registers, and so this is going to be treated as an unsigned number. Now what we've basically got here is some branch options we can use. So branch on high, branch on low, branch on equals, branch on not equals. And these are sort of macros, if you will, so pseudo operations that will perform the branches. Now for the purpose of testing, we've got these routines that will show to the screen which branch actually occurred. Now if we execute this now using this logical comparison, let's see what actually happens. Okay, so we've got an L shown to the screen. Now, one other important thing to bear in mind is, as I've said before, is basically our condition code register is just 2 bits, so it can only have a value of 0 to 3. And what that actually means entirely depends on what the previous command was. So basically our condition code is just these 2 bits of the secret PSW register. And as I say, these basically give us a value of 0 to 3. And what that 0 to 3 means is entirely dependent on what our previous commands were, which is why we've got sort of pseudo operations to perform the actual jumps. Now here we've done a logical comparison between R1 and R2. Now the logical means unsigned. Now in this case R1 is lower than R2, and so the branch has occurred and the L has been shown. So it will be this execution that actually occurred here. Now if I changed this value here and I changed the second value to 7 and lots of zeros as well, now these two obviously contain the same value now, and so in this case it will be this branch that has occurred, and so we show the E to the screen. Now you can see the condition code is actually 0 here, and the condition code in most cases for most kinds of mathematical operation means equal, so that's why that has occurred there. Now if we just change that back a second here, and this time instead of a logical unsigned comparison we use a signed comparison. So CR is a signed comparison between these two. Well, this time R1 is actually going to be higher than R2, because that is actually, if this is a signed number, that is actually a negative number. So this time if we run again, we've actually got an error message. I think my code comment is in the wrong position. Okay, it was actually this line. This line was too far to the right, and it was actually hitting the continue column apparently. So I've made this line a little bit shorter here by removing some of the white space here. It's really difficult when the column positions have special purposes and you're trying to comment your code as effectively as possible. Anyway, getting away from the point there. So this time R1 is actually higher than R2 because R2 is a very small number this time. And so branch if higher has occurred this time, and that has shown the H to the screen. You can see CC2 is set here. CC2 means that R1 is higher for comparison commands in this case. So that is why that has occurred. Now, of course, if we comment out, we're using the star symbol at the start of our lines here. So if we comment out these two here, so we're no longer looking at higher and lower. And this time, if we just look at equals and not equals, we've got no errors, so that's a good sign. And you can see here, this time we've been told that these two are not equal, which is entirely true. And of course, this time CC equals 2, which again is related to the higher here. And again, it's just the macro that we use that decides which one actually occurs here. Now, in those cases, we've been comparing registers here, CR, CLR, the R at the end signifies registers, but we can compare memory addresses, and we have a variety of options depending on what actual comparison we want to do. So we have compare for comparing 32-bit signed numbers, compare logical for unsigned numbers, and compare half. And what this does is it compares a 32-bit value in a register to the address here, which would be specifying a half at that address, which will be sign extended. So the registers are always 32 bits, but the memory address may or may not be. Now, as I say, I'm not going to try those out here. It's exactly the same functionality-wise for the branching as comparing to registers. As I say, you're welcome to try out the more complex combinations yourself. I would advise you to do so. If you don't want to, that's fine, but assuming you are actually going to write your own code at some point, you're gonna figure this out anyway. You're simply going to have to, because at the end of the day, you will have to do this kind of thing in your own code, whatever your code is trying to do. Now, those commands you saw before, these sort of very logically named branches, these are actually macros for a far more complicated command. Now, this command takes advantage of the fact that the condition codes are basically just 4 possible values to just 2 bits. And what they do is they allow you to create a custom command that will branch if any of those values are contained within the condition codes. And so those macros we saw before, the branch if higher, branch if lower, they're not equals, that kind of thing, are actually all macros for the BC command. Now, this takes a 4-bit command, but that's not a comparison to the 2 bits within the condition code as such. Each of those bits is a possible value that the condition code can contain, and if those values are true in the condition code, then the branch will occur to the place that we specify. So, for example, here, this bit on the left is equivalent to the value 0 in the condition codes. The next one's 1, the next one's 2, and the next one's 3. And so what we're specifying here is that we will branch if the condition code contains a 0 or a 2, and we will branch here and we'll show true. Now, if we run our example here, and we see what the condition code actually contains here, so we're just running now. So in this case, the CC register contained the value 2, and we've set the bit relating to 2 in the condition code to 1 here, so the branch has occurred, and we've shown T to the screen, so for T for true. Now, if I change the code here and I remove the 0 here and run this again, well, we will now get a value of F shown to the screen because we didn't branch away, and so we ended up flowing into the code that shows the F. So we can create our own custom branch based on the possible values within the condition code, and of course it's going to entirely depend on what our last comparison was here. So if we just change this here, and this time we're doing a logical comparison here. And so the logical comparison has resulted in the condition code containing the value 1. Well, again, that relates to this bit. That's a 0, so this branch won't occur. Now, again, I mean, I think in most cases, you're really going to want to use the pseudo operations. There's almost infinite number of them. They're all tailored for the various kinds of commands you might want to run. So again, the condition codes are set with different values depending on the previous command. So if you're doing a comparison command, you want to probably use one of these. If you're doing addition, subtraction, addition, that kind of thing, you would probably want to use one of these. And if you're using a test command, you would probably want to use one of these. But as I say, they all actually end up effectively being one of these kind of commands anyway. So if you really want to get clever, you can use this instead. Now, the possible values you pass to it here, basically, as I say, this is the equivalent mask, and these are the equivalent condition codes that will cause a branch here. I've shown a variety here just to kind of make it clear what this command is actually doing here, and the equivalent macros that you might use here. And an interesting one is no-op is often, depending on your assembler, is often a conditional branch that just can never occur. And branch always is effectively this here, where whatever the condition code mask contains, we're always going to branch. So I'd say just some interesting factoids there for you. And as I say, I'd strongly suggest you download today's example and you try out lots of them yourself. I always suggest that anyway, because you know, with the best will in the world, when I was doing the 68000, when I started to learn that assembly language, I spent a couple of weeks reading all of the books I could find on it, and you get quite confident. You think, oh, you know, I know Kung Fu now, kind of thing, like the old Matrix thing. But it doesn't work. You can't learn. You can't learn these things just by watching hundreds and hundreds of videos and reading hundreds and hundreds of books. At least I can't. So you have to try it out yourself, and it's then you will start to through bitter mistakes, you will start to learn how it all works. So please go ahead and download the source code and the build scripts and the pre-configured simulator, the Hercules emulator. You can set up your own by all means, but as I say, I'm hoping you can use mine as is, and that will help you play around with the system and get started really quickly. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.